Welcome back. In my earlier video, I had discussed about sequence of function. I had discussed uniform convergence of sequence of function and the relation uniform convergence of sequence of function and differentiable. Today I will discuss the Riemann integration. We all of us know integration I had done in 12th standard, also 10th standard. Riemann integration here actually the name of the mathematician Riemann. Integration actually the concept of area. Here Riemann integration actually deal with the finding the area of the integration a to b fx dx. Mathematician Riemann had researched about this integration. So this integration is called Riemann integration. Here actual idea is concept of area. We all of us know if A belongs to R2, then the area of A computable if A is rectilinear boundary. As for example, consider triangle, square or any. We all of us know the area of triangle is half base into height and rectangle is base and breadth, and in this picture I can draw many triangle here. So this is the area of this picture. Riemann integration actually defined for any function. Here the function is defined from closed interval ab to r. Then graph of f equal to x fx where x belongs to AB. This is geometrically deal finding the area of x equal to a line, y and x equal to b line, y equal to 0 line and y equal to fx. We have to find area of this region. Are you getting actual the conception? Okay. Here the main idea is, notice here the interval closed AB. At first, partition each interval is such type a equal to x naught less than x1 less than x2 up to xn equal to b. At first partition the point a equal to x naught, x1, x2, x3 up to xn equal to b. This is xn minus 1 such type. Now draw some vertical line and I will draw up to the graph. Are you getting? Notice this look like a rectangle, but one side of the rectangle is not a straight line because this is the curve. Then I start from this line, from this and go on this. Okay. Notice here one thing, these rectangle are below the function. So if you find the area of this rectangle and bound them together, then added sum of these areas of rectangle is less than equal to area of the region below the graph of the function. Okay. Now we can also draw some rectangle. Here the idea is, take the higher point of this rectangle and draw this rectangle, and if you find to area of this rectangle and sum them, then sum of this bigger rectangle is always less than equal to graph of the region inside of this function. Okay. If you notice this rectangle, here notice, here the weight is just sub interval, here the height is minimum value of the function. So define small mi which is equal to infimum of fx where x belongs to subinterval xi minus 1 to xi. Okay, where I grows from 1 to n. And for this rectangle, similarly define capital Mi equal to supremum of fx where x belongs to closed interval xi minus I to xi where I belongs to closed n to 1. Are you getting the idea? Well, here one thing more noticeable, area means the curve which is bounded by x equal to a, x equal to b line and y equal to fx and y equal to 0 line. This is always less than equal to sum of areas of circumscribing rectangle, means this area and which area always greater than equal to sum of the rectangle inscribed by the region. That means this area, this is always less than equal to the area bounded by x equal to 0, x equal to b, y equal to 0 line and y equal to fx. Are you getting the idea? Well, here the upper Riemann sum is defined as UPF, which is defined as summation I equal to 1 to n capital Mi times delta xi, where delta xi equal to xi minus 1 and lower Riemann sum which is denoted as LPF, which is defined as summation I equal to 1 to n small mi times delta xi, or similarly delta xi equal to the weight xi minus 1. Are you getting? From this notation it is obviously always true LPF less than equal to the area A, which is also less than and this area also less than equal to upper sum UPF. For example, consider fx equal to x where x belongs to 1, 5. That means we all of us, this is the line y equal to x. First subdivided this interval 1, 5. This is 1, this is 2, this is 3, 4, 5. Here I have taken one partition. This is p equal to 1, 3 over 2, 2, 3, 4, 5. Okay. That means here also 3 over 2. That means this picture would be such type. This vertical line which does the graph y equal to x. Are you getting? For this picture, the value of LPF would be, just think, this height would be 1 and this distance would be half. That means 1 times half plus this distance is 3 half times this distance would be half plus here this height would be 2 and this distance is 1. That means 2 times 1 plus here notice this distance is this height would be 3 and this distance is 1 and for this height would be 4 and this distance is 1. If you calculate the value, then this value would be 37 over 4. UPF would be here for first rectangle height would be 3 over 2 and base would be half, plus for second rectangle, notice here the height is 2 and base is half, plus for third rectangle, here the height be 3 times 1, plus for fourth rectangle, here the height would be 4 plus 1, plus for fifth rectangle, here the height would be 5 times 1. Okay? This value equal to 55 over 4. And notice, since I have got LPF equal to 37 over 4 and UPF equal to 55 over 4, then obviously this is greater than LPF. Are you getting the idea clearly? Well, now I will tell one new concept. A partition Q is called a refinement of a partition P if P contain Q. All the points of P are also points of Q, but in Q maybe more points exist. As for example, I have defined the partition P equal to A equal to x0 less than x1 less than x2 up to xn equal to b. Notice in Q I have added one more point, x double dash. So obviously P contain Q because Q contains more point than P. So obviously P contain Q. So Q is refinement of P. Are you getting the idea? Well, when P contain Q, then obviously if you notice the graph, then LPF less than equal to LQF. What is the meaning? See the graph. Here notice this is the LPF, but when we will add the more point, here I have add x dash. So this is the refinement of P. Then the contribution of lower sum would be now such type rectangle. This picture tells us lower sum will be increased when we refinement the partition. Are you getting the idea? Well, that means when P contain Q, then LPF always less than equal to LQF. And this proof is very easy type proof. Try to oneself. This when P contain Q, then UPF always greater than equal to UQF. Because in this picture, obviously, notice this is the UPF, okay, but when I will add here this point extra, then UPF would be this part. That means, notice the picture, this is the earlier UPF, earlier rectangle, now the rectangle is this part. Means when I have added new points, then this part have removed here. Means when P contain Q, then UPF greater than equal to UQ. That means when I will added more point, then upper sum will be decreased, but lower sum will be increased. Now I will see some interesting thing also. I have defined, F is defined here from close interval AB to R, and I have defined capital Mi equal to supremum of the function fx, where x belongs to in the interval close interval xi minus I1 to xi, and small m I be the infimum of fx where x belongs to close interval xi minus 1 to xi. Here since function is defined from close interval ab to r, so obviously this function is bounded function. That means there exists capital M and small m such that capital M greater than equal to fx and fx greater than equal to small m, where this capital M is the supremum of the function where x belongs to close interval ab. Notice here capital Mi and capital M both are different, and small m be the infimum of this whole function where x belongs to ab. Here small mi also and small m also be different thing, because here capital Mi and small mi be the supremum of every sub interval, but here capital M and small m, capital M be the supremum all whole function and small m be the infimum of whole function. One relation will be established. Capital M times b minus a always would be greater than equal to UPF, and UPF always greater than equal to small m times b minus a. Also, capital M times b minus a greater than equal to LPF, and LPF is greater than equal to small a times b minus a. And this is true because Mi always less than equal to capital M, small mi always greater than equal to m. So we can tell, just multiply it b minus a. So we can capital M times b minus a always greater than equal to UPF, and UPF greater than equal to LPF, and LPF greater than equal to small m times b minus a. Are you getting the relation? Well, now I will define one new concept, least upper bound of all LPF, where P is the partition of the AB, and this is called as lower integrable of f in the set closed AB. See, and this is the lower integrable of f because this is the LUB of the set LPF. Now I will going to see the new concept, upper Riemann sum, which is equal to infimum of all the set UPF, since the function is defined as close interval AB to R. So obviously there exists a infimum of the all UPF, and this infimum is called upper Riemann sum, which is denoted as integration a to b bar fx dx. Are you getting? Well, we will define the lower Riemann sum, which is actually supremum of the set all LPF, and this is defined as integration a bar to b fx dx. Are you getting? Well, a function f which is bounded is called Riemann integrable over the closed interval AB if the upper Riemann sum equal to lower Riemann sum. And then we define this notation, integration a to b fx dx, which is same as upper Riemann sum and lower Riemann sum. Are you getting the idea? Well.